When most of us think about Earth science, we picture geologists out in the field, hammering away at rock formations, or studying localized layers of dirt and crust. Treating our planet like a closed box ignores the external forces that define our environment. The ground beneath our feet does not exist in isolation. To map out the forces driving our weather, oceans, and tectonic plates, we have to start by stepping off the surface and looking out into the wider solar system. By examining the extreme environments of our neighboring planets, we can identify the specific physical rules governing our own home. This approach frames the natural systems keeping us alive as components of a much larger, interacting celestial machine. Around 4.6 billion years ago, our solar neighborhood violently condensed out of a single spinning cloud of gas and dust known as the solar nebula. As these early planets formed, they underwent differentiation. The heaviest metallic elements sank inward under gravity to form dense cores, while lighter materials floated outward to form mantles and crusts. Because of that shared birth, our planet carries the same chemical DNA, the same building blocks of iron, silicates, and carbon found across the rest of the solar system. Yet, despite starting with these identical raw materials, the outer environments of these worlds evolved in vastly different directions over the ensuing eons. This shared origin makes our solar neighborhood a laboratory. When we point our telescopes at nearby planets, we are seeing the results of different variables applied to the same basic chemistry. Take a look at this image of Olympus Mons on Mars. The massive central caldera and sprawling ridges reveal a geosphere that has lost its internal heat, leaving behind these extinct, towering volcanic structures. On Venus, we see swirling, unbroken cloud patterns. Its dense atmosphere traps solar radiation, raising surface temperatures enough to melt lead. Further out, Jupiter shows the immense turbulence of the Jovian giants, defined by distinct horizontal atmospheric bands and massive swirling storm centers. These gas giants complete a full rotation every 9 to 10 hours. As we see here on Neptune, that fast rotational speed acts as an engine, whipping up high-altitude clouds and sustaining winds that move at hundreds of kilometers per hour. Measuring those extremes helps us understand why our own home is hospitable. Earth's 24-hour rotation and moderate atmospheric density are the specific variables that keep our climate system stable. We can also see how celestial mechanics actively manipulate the Earth on a daily basis. As Earth revolves around the Sun, it maintains a 23.5-degree tilt relative to its orbital plane. That angle is the mechanical driver of our seasons. This tilt forces solar radiation to hit the summer hemisphere head-on, while the same light disperses over a wider, cooler area on the winter hemisphere. Then, the Moon. It operates in synchronous rotation, keeping one face pointed at Earth as its gravity tugs our oceans. The freezing winters, the monsoon rains, and the daily shifting of the tides do not originate on Earth alone. They are forced by these external, space-based mechanisms. Ultimately, everything on our planet operates on an energy ledger, a balance of incoming solar radiation, lunar gravity, and the internal heat radiating from our core. You can see the explosive, raw power of the Sun in this image of a massive solar prominence erupting into space. That continuous output of energy fuels our entire water cycle and the growth of the biosphere. Environmental insight is the realization that planetary systems are not static. They are continuous cycles of matter and energy, where a shift in carbon or heat can move the entire planet toward a new climate state. From space, we see a vibrant, living network of interconnected systems. We study the stars and our neighboring planets to map the boundaries of the unknown. We use that cosmic perspective to become effective, scientifically literate protectors of our own home.